today we are going to move on with actual estimation of the data. So from now on, we are going to think of some probabilistic model or probabilistic method to evaluate the data or estimate the data. So we are supposing there will be some set of data given, and we want to analyze them. Well, the first step of the analysis is quantifying them. So we want to analyze them and try to express the data in terms of the number. Speaking of density estimation, there are two big approaches. So one is parametric approach, the other is non-parametric approach. So today we are going to start our discussion from here, parametric approach. But before we touch anything, well, let's first talk about the framework. So we are going to talk about some method to estimate the data probabilistically. So you have given a set of data, and we are not yet supposing there will be any label or any annotation. So it's basically unsupervised nature. We are supposing data set D will be given, and as before, they are indexed by 1 to n. And again, we don't suppose any label. So basically, each data instance only consists of X or set of attributes. And speaking of these variables, each element, well, these individual variables can be continuous or discrete. So what we want to do in this section is something like this. So we are going to consider the input ranges. So data appear certain ranges of my domain. In other words, we are going to consider the sample space. So speaking of this kind of distribution, sample space is maybe the underlying axis. And based on the actual observation, so the big assumption is there is a true distribution. And from this true distribution, we are sampling our data. And this is the observation from the truth distribution. And we want to do something in reverse way. So what I mean by that is based on the observation, we want to reconstruct the original distribution. So at the end of the day, what we want to have is something like this. So again, this axis is a sample space. So if any value on the sample space is given, we want to return the probabilistic quantization. So this probabilistic quantization is called as likelihood. So this is in general what we are trying to do. And this theme is repeating again and again. So well, if you don't understand 100%, well, it's okay. So well, please try to remember there is a true distribution, and that generated n sample. And based on that n sample, we want to reconstruct the original probabilistic distribution. And there is a big assumption while we are doing this. And the assumption is holding most of the machine learning algorithm. So that is an IID assumption. This is really, really important. So IID assumption is independently, identically distributed. So well, even if I gave you the full name, it's really hard to figure out what it means. So first of all, independent. So we are playing with the n sample. And well, big assumption here, these n samples are independent from each other. That means, well, knowing data point 3, oh, sorry, D3. So knowing data point 3 does not affect any probabilistic knowledge about knowing D1, for example. So we spoke about the definition of independence before, where all the definition, all the rules relate to independence applies here. So where any given two instances from my sample, where they are independent from each other. Well, second item here, identically, we assumed there is a true distribution. And this true distribution does not change it, even if you draw a sample. So where you have n samples, they are all coming from the same distribution. So this is the definition. So you have n samples, something like this, where they are all coming from the same origin. At the same time, knowing one guy does not affect knowing the other guy. So that is a big assumption that we want to remember over the semester. So IID assumption is that important. So let's get into what density estimation is. So there are two types of density estimation. One is parametric, the other is non-parametric. And parametric density estimation, where we assume that there is a true distribution. And in terms of expressing this true distribution, we are assuming there is a certain template. So parametric approach assume there is a template, and this template has some empty space named parameter. So if you know the parameter for the sample, then you can express the distribution of that sample in terms of the template of your choice. So this is the basic idea of parametric approach. So we want to, again, formally, we want to assume there is a functional form fixed for the distribution. And this fixed form of the distribution has a set of parameters. And our goal from now on is to find out what these parameter values are. So we are going to see this soon, but where if you assume your true distribution is a Gaussian distribution, then you want to find these two values from the data, mean and covariance. So this is just a simple example, and we are going to get into it. On the other hand, we are going to study non-parametric method as well. So non-parametric method, where the big component in parametric approach was assuming the template of your true distribution. For non-parametric approaches, we don't assume there is such a template. Instead, we want to evaluate the probability estimation based on the older samples in my data set. When I write down PROB, that means probability. So probabilities are estimated using all data samples. So well, this is still quite vague, so we want to find out what this means next week. But here comes some examples. So let's quickly preview what those examples are. So one is a histogram. So given data set, you can express your data distribution using fixed size of bars. And if you have plot of these bars, basically representing the occurrence of your data within certain ranges, where that is a histogram. And where there is another well-known approach that is kernel density estimation. So we are going to study these two next week. On the other hand, well, actually this diagram is comparing parametric estimation and non-parametric estimation as well. So histogram, like we just discussed, this is non-parametric, but Gaussian can be displayed like this, where that is a parametric approach. So let's find out what this means more in detail. So today we are going to cover parametric methods. So parametric method, again, there exists a true value for your choice of template. So our goal is to find out those true values of parameter. But at the same time, our big assumption is, well, you cannot find out the exact value for the true parameter. The setting is like this. So you have set of random variable, so basically vector of x. And model distribution is expressing the probabilistic distribution of your data space. And the goal is, well, given set of parameter, we want to find out the probability of the data. Again, this is a given parameter, estimate the probability of data. This is called as likelihood. So we are going to take a probabilistic approach. So we first want to quantize our data sample in terms of the probability. And in certain way, we want to maximize that quantity by adjusting this theta parameter. So here is a big assumption. If you find out the right choice of parameter theta, then your likelihood will be maximized. So this is a big rule in parametric method. So this simple rule is ruling the entire section of parametric method. And since it is that important, it has a name. Maximum likelihood, or simply ML. So maximum likelihood is to find out right choice of theta that maximizes the likelihood of my data. And let's refresh the slide and make the space clean and take one additional discussion. So last class, we talked about the probability of multiple independent units. And in the previous slide, we assumed all the data points, they are independent from each other. So basically, we have n samples, and maximum likelihood method is to maximize probability of the data given theta, which is the parameter. And we want to adjust theta to maximize this probability quantity. So, well, I'm repeating again and again, this is so important. And we want to express this in terms of individual data points. Otherwise, we cannot estimate it. But there was a big assumption. So each data points are independent. So we can express this as maximize probability of D1 theta multiplied by probability D2 theta and so on until all the way to the end theta. So each individual independent from each other, we can express the probability of the data set in terms of the product. And next thing we want to do is find out theta that maximize this quantity, this multiplication. Well, here is the following question. So another issue is, well, each of these are relatively small values. So this is the probability. So it is somewhere between 0 and 1. Somewhere between 0 and 1. Somewhere between 0 and 1. So if you have number like this, so if you have fractional number multiplied n times, oftentimes you are reaching to a numerical underflow. That means you're going to express really small number like 0.0000 some number. And well, computers cannot express these kind of small number properly. So here comes logarithm trick. So we are going to take the logarithm of everything. So instead of simply maximizing this guy, we want to maximize log of those likelihood quantity. Let's remove those handwritings again. And let's take a look at this chart. So probability again, maybe like this. So this is the graph of log. And our probability value is ranging between 0 and 1. So we only interested in these ranges. So the outcome of log probability is somewhere between here and actually never ending. So it is ranging between negative infinity to 0. So original probability space 0 and 1, we are transforming our playground from 0 and 1 to negative infinity to 0. So, well, this is what is going on. So formally define maximum likelihood estimation. So ML is where you first quantize likelihood and you want to evaluate your likelihood of data based on the parameter value. And given that, you want to adjust the parameter so that you can maximize the likelihood. So this is a method of estimating parameters of the model. And well, this is the expansion that we just take. And well, here is the issue that we discussed. So what's going to happen in your probability space? So say this is the quantity in terms of probability. Then this is the quantity after you take the logarithm to your probabilistic values. So where things are quite narrowed down because we are shifting the value ranges from 0 and 1 to a certain value after taking log. Where the point that I want to discuss though, where the pattern of increasement or pattern of decrease, where it does not change even after you take log. Well, that is because log is monotonically increasing. Monotonically. Again, the maximum location does not change even after you take the log. So that is the idea of maximum likelihood. And then, well, given the idea of maximum likelihood, let's move on to the actual distribution model. So let's take few of them and let's move back to the Bayesian parameter estimation. So, well, we are at page 13 now. So we are talking about density estimation. And within density estimation, we have parametric method and non-parametric method. And within the group of parametric methods, where there is models or methods for discrete random variable, and there is models for continuous random variable. And here are they. So here are a few examples of discrete random variable model. So you have more, much more actually. But here are well, 3 common examples. So Bernoulli distribution, binomial distribution, multinomial distribution, and we will see soon. So basically, we think of well, dice tossing or picking a card from your playing card. There is expected outcome like 1, 2, 3, 6. Basically, these are discrete outcome. So in this case, your outcome is discrete, and we want to model the probability of each. In this case, we use well, models for discrete random variable. Well, let's think about some continuation of time, continuation of distance. So basically, there is no clear cut between different values, and you can go into where more precision different so that you can have infinite closeness or distance. So well, if you play with those continuous value, then you need a model for continuous random variable, and here are the example. Here are some exceptions though. So uniform distribution, there is a discrete version and continuous version as well. But we only speak about the continuous version. And there are lots of assumptions and lots of background, so well, please bear with it. Next thing you need to know is the notation. So where in density model or any probabilistic distribution, we use this kind of notation a lot. So there is a tilde in the middle, and where this guy is well, probably new to some of you. Well, anyway, we use random variable, where in this case x is sampled from a distribution. When I write down simply dist, that means distribution. So x is sampled from a distribution, and the type of the distribution is n. That means this is a normal distribution or Gaussian distribution. And this guy has a parameter. So those parameters are explaining the characteristic of the distribution. So normal distribution is parameterized by mu and sigma square. So if I have collection of these values, it will form a shape like this. So this is what the notation implying to me.